Welcome back, Physics 30. This is section 26-3, Simultaneity. And as we saw earlier there, an important consequence of the theory of relativity is that we can no longer regard time as an absolute quantity. No one doubts that time flows onward, never turns back, but according to relativity, the time interval between two events, and even whether or not the two events are simultaneous, depends upon the observer's frame of reference. And by an event, which we use a lot here, we mean something that happens at a particular time and place. All right. Two events are said to occur simultaneously if they occur at exactly the same time. But how do you know two events occur precisely at the same time? If they occur at the same point in space, such as two apples falling down on your head at the same time, it's easy. But if the two events occur at widely separated places, it's more difficult to know whether the events are simultaneous, since we have to take into account the time it takes for the light from them to reach us. So for example, if you see a distant star explode in the night sky, of course that light has reached your eye at Earth, but it may have taken years to reach your eye. So that star may have actually exploded years ago. And in fact, anything you look at in the sky, you're actually looking at the past, because you're getting that light receiving you, but of course that light had to travel a large distance. Because light travels at a finite speed, a definite speed, a person who sees two events must calculate back to find out when they actually occurred. For example, if two events are observed to occur at the same time, but one actually took place farther from the observer than the other, then the more distant one must have occurred earlier, and the two were not simultaneous. So let's take a look here. So for example, we have person O looking at two events, A and B. Now if this distance is the same thing as this distance, and we see the lightning strike at the same time from both parts, then yes, we could say they're simultaneous, because the distance is the same and the time in which we see the lightning is the same. So that would be a simultaneous event. We can now imagine a simple thought experiment. Assume an observer called O is located halfway between A and B, where two events occur. Suppose the two events are lightning that strikes the points A and B. As shown, for brief events like lightning, only short pulses of light, and they're represented by these blue curved lines here, will travel outward from A and B and reach O. Observer O sees the events when the pulses of light reach point O. If the two pulses reach O at the same time, then they had to be simultaneous, because the distances are the same and we're seeing the light at the same time. And because light travels at a finite speed. So this is because they travel at the same speed, i.e. postulate 2 from earlier here, the idea that, yes, the speed of light principle, light goes through empty space with a definite speed, no matter what the source is doing or the observer. And the distance OA equals OB. So the time for the light to travel from O to A and from B to O must be the same. Observer O can definitely state that the two events occur simultaneously. On the other hand, if O sees light from one event before the other, then the former event occurred first. So nothing too crazy there. But what happens when one of these objects are moving? Like if we look over here, the question we really want to examine is first, is this: if two events are simultaneous to an observer in one reference frame, are they also simultaneous to another observer moving with respect to the first? Let's call observers O1 and O2 and assume they are in a fixed reference frame 1 and 2 and move with speed v relative to another. These two reference frames can be thought of as two rockets or two trains. So here we have O2 sees O1 moving to the right with a certain speed, and vice versa. O1 could just as easily say, oh, actually I'm not moving, you're moving to the left. So both of those scenarios would be synonymous. And over here I highlighted the point, both viewpoints are legitimate. So observer O can okay, so we're over here now. So we have the two observers. These two reference frames could be thought of as two rockets or two trains. So O2 says O1 is moving to the right with speed v. O1 says O2 is moving to the left. And both viewpoints are legitimate. There's no third point of view to tell us what's actually going on. So both of those statements are good. Okay, if we go over here. Now suppose that observer O1 and O2 observe and measure two lightning strikes. The lightning bolts mark both trains where they strike. It A1 and B1 on the first train and A2 and B2 on the second train. For simplicity, we assume that O1 is exactly halfway between A and B, and O2 is exactly halfway between A2 and B2. Let's first put ourselves in O2's reference frame. So we observe O1 moving to the right with speed v. Let's assume that the two events occur simultaneously in O2's frame, and just at that instant when O1 and O2 are opposite. So they're right at this point. O1 is moving to the right, but for the moment, when they're right across from each other, the lightning strikes both cars at those locations. Short time later, light from A2 and from B2 reach O2 at the same time. Since O2 knows or measures the distance between here and here is equal, he or she knows that it's simultaneous. And this cart's not moving. Lightning strikes. The light from B2 hits O2. The light from A2 hits O2, and it happens at the same time, as you see in this picture here. So O2 would say, "Yep, lightning struck A2 and B2 at the exact same time." Okay, but what does O1 see? From our O2 reference frame, we can predict that what O1 will observe. We see that O1 is moving to the right, of course. During that time, light is traveling from O1 to O1 from A1 and from B1. So light is traveling from there. As we can see from our O2 reference frame, that the light from B1 has already passed O1, and light from A1 hasn't reached O1 yet. Interesting. So given that light travels at the same speed in any direction and in any reference frame, and that the distance O1, this distance equals this distance, then observer O1 can conclude that the lightning strike B1 happened before the lightning struck A1. The two events are not simultaneous for O1, even though they are for O2. So if we're talking about regular speeds, everyday speeds, 100 kilometers per hour, the speed of light is much quicker than 100 kilometers per hour. So for all intent and purpose, these events would be simultaneous for both people. Because 100 kilometers per hour compared to lightning striking or the light traveling, there wouldn't be a difference. But if this cart was moving at close to the speed of light, then that effect would be seen, in which simultaneous for one person would not be simultaneous for another person. So that's a little point I make over here. At everyday speeds, there's more agreement on events appearing to be simultaneous, but at large speeds, close to the speed of light, however, there is a disagreement on events being simultaneous. We thus find that the two events which take place at different locations and are simultaneous to one observer are actually not simultaneous to a second observer, who moves relative to the first. So, of course, the next question is, well, who's right then? The answer is they're both right. There is no best answer. There is no best reference frame of reference when choosing which observer is right. Both frames are equally good, because since this one is moving at a constant velocity, they're both inertial reference frames, so both are equally valid. We can only conclude that simultaneity is not an absolute concept, but is relative. It depends where you are, especially when we're dealing with moving at very high speeds, close to that of the speed of light. And of course, we are not aware of this lack of agreement on simultaneity in everyday life, because the effect is noticeable only when the relative speeds of the two reference frames is very large, near that of the speed of light itself, or the distances involved are very large. Okay, so we don't see it happening. Like even with this train example, trains moving at regular speeds is very low compared to the speed of light. So the speed of light would be very quick, and O1 and O2 would say, yep, they happened at the same time. But if this cart was moving much faster, close to the speed of light, we would get this weird scenario happen in which O2 sees the light coming at the same time from either side, but O1 is moving so fast that actually doesn't see A1 until B1 is well past it. Right. We'll stop there, and in the next part we'll look at 26.4 time dilation in the twin paradox.